Hey, this is Mr. Colburn. I'm reporting this on Monday night, so not sure what exactly we'll do in class tomorrow in terms of this packet. Maybe I go over some stuff that I go over in this video. But to leave off, or sorry, to pick up with this problem where we left off in class on Monday, we discussed that the way to find x-intercepts is to replace y with 0 and then solve. And so that's what I did here in the pink. I replaced the y with 0. I then multiplied both sides by x minus 3. And on the left, 0 times anything is still 0. And so now I'm just left with a quadratic, which I factored and solved. When I solved it, I got two answers. I got x equals 3 and x equals negative 2. But again, as we discussed in class, x equals 3 is not actually in the domain because that causes us to divide by 0. So essentially, even though the numerator is 0 when x is 3, so is the denominator. And 0 divided by 0 is not 0, it's not 1, it's undefined because you can't divide by 0. So that means we actually only have one x-intercept at negative 2. To find y-intercepts, replace x with 0, then I evaluated and got 2. Okay, so now, before I find the range, I'm actually going to try to put together a sketch of what we know so far. So we've got our x-intercept is at negative 2, and our y-intercept's at positive 2. And I also know that at x equals 3, we're not going to have a point on the graph that lives at above or below this x equals 3. So what else do I know about this graph? Well, what is its shape? It's a parabola divided by a line. It's a quadratic divided by a linear function. What does that even look like? Well, you may remember from math analysis that this is called a rational function. And when you have a rational function, you can try to divide the two pieces. So I already factored the top as x minus 3 and x plus 2. And if I rewrite this factored, then I see here I have an x minus 3 on top, I have an x minus 3 on bottom. Technically, I'm dividing x minus 3 divided by itself. And so that's 1. And so what I'm left with is 1 times x plus 2. You may also know this as canceling. And so what I am left with is this expression is equal to x plus 2, with the little caveat that we know x can't equal 3. Because again, if x were 3, then the function would be undefined. So at every point except x equals 3, our function is the function x plus 2. So essentially, I have a straight line. It's got a slope of 1, it's got a y-intercept of 2, and when it gets to x equals 3, there's a little piece missing. We call this a hole. You can probably imagine why it's called a hole. Another name for it is a removable discontinuity. Discontinuity meaning the function's not continuous at this point, and removable meaning essentially when we cancel here, we can create a function that's identical to the original function with the discontinuity removed. Anyway, we'll talk more about that later. Lastly, let's talk about the range. Now that I have a nice sketch of my graph, the range is all of the y values that the graph takes on. And it's the graph of a line. And it goes up forever and it goes down forever. So it takes on every y value imaginable, except for the y value that lives where this hole is at 5. So the range is that symbol means all real numbers, basically every number that you can think of that's not imaginary, like 0 or 10 or 20 billion. So every real number is part of the range. Every real number is a possible output of this function, except y cannot equal 5. That's how we would write that. If this notation's funky, that's okay. You can just write y doesn't equal 5. Or you can write it with words. Okay, moving on. I think we also discussed this function a little bit. So we definitely discussed that because you can't square root a negative, I took the inside of the square root, this x plus 3, and I said x plus 3 is less than 0, meaning x plus 3 is negative, to investigate when that's true. Subtracting 3 from both sides, x is less than negative 3. That causes the inside of the square root to be negative, and so that is the problem area. That is what is not in my domain. So what is in my domain is all the numbers that don't have x less than negative 3. Or in other words, all of the numbers where x is greater than negative 3 or equal to negative 3. Negative 3 is the endpoint here, the x value of the endpoint on our square root function. It goes off to the right. It does not go off to the left. Hopefully, we have seen the square root function before. This one, by the way, is in graphing form. All right, moving on. We have ourselves, it looks like a square root function, but it's got an x squared in it. So maybe you recognize this, maybe you don't. I don't really know how much we talk about this in math analysis, but here's what we're working with. And if it's not familiar to you, if you can't tell the shape of it by looking at it, imagine what would happen if you square both sides. And then add x squared to both sides. And maybe even, oh, I'm sorry, you can't see this. You can't see this. So again, I squared both sides here, the square root, and then I subtracted or added x squared to both sides. And then, honestly, let's rewrite 25 as 5 squared. Do you see it yet? This is the graphing form of a circle. It has a radius of 5, and because there's no h or k value, its center is at the origin. Except when it's written as it is before I squared both sides, the y value is equal to the positive square root of whatever this is. So it's actually only going to be the top half of the circle because it's a function, right? The circle in graphing form is not a function. It fails the vertical line test. There's more than one y value for each x value. But the original equation is a function because it's only the top half of the circle. It does not fail the vertical line test. There's only one output per input. So we have our center at the origin, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. that is a sketch of our function. And so just by looking at the sketch, I can already fill out all of these questions. If I didn't know that this was a semicircle by looking at the equation, again, we could use our other strategy, plugging in 0 for x, plugging in 0 for y, and we'll get the same answers. The x-intercepts are 5 and negative 5. The y-intercept is only positive 5 because, right, y equals the square root of something. The square root of any number has to be positive. So we're not getting negative 5, we're only getting positive 5. The domain, remember, is the possible x values. And so we have x values ranging from negative 5 all the way up to positive 5. I'm going to say the domain is all real numbers such that negative 5 less than or equal to x less than or equal to 5. Again, you don't need to write the all real numbers symbol. It's implied in this class that we only deal with real numbers. In higher level math classes, that's not a guarantee, and so sometimes you have to specify that we're only talking about real numbers, but here it's not super necessary. And so the range would be y values that lie between 0 and 5, inclusive, so or equal to 0, or, sorry, y is greater than or equal to 0, less than or equal to 5. This next function is a little bit funky. I don't think you see things like this in math analysis. I could be wrong, but it has an absolute value in it, but it's not just like the absolute value function. There's more going on. It's the absolute value of x divided by x. And for this, we're going to rely on the definition of absolute value. The absolute value of x, by definition, and we'll talk about this more as it becomes more useful. Whatever's inside of the absolute value bars is always positive. So if it's already positive, then it just equals itself. And so the absolute value of x is the same as x, so long as that x value is not negative, 0 or positive. If x is negative, meaning it's less than 0, then the absolute value changes the sign. So if x is negative 5, the absolute value of that would be positive 5. And so we're going to write x, but with a negative sign in front of it to indicate that the sign changes. Using this definition, I'm going to rewrite our function as a piecewise function. So if x is positive, then the numerator is simply 3x. If x is negative, then the numerator becomes 3 times negative x. And I'm going to sort of clean up both the top expression and the bottom expression here. I'm going to erase the definition. Feel free to pause, go back if you need to look at it again. So here, 3x over x is just 3. And that's true, again, whenever x is greater than or equal to 0. But it's actually not true when x is 0. 3x over x is not the same as 3 when x is 0. Because when x is 0, this division by x causes the function to be undefined. So this expression for any positive value equals 3. At 0, the function's undefined. And 3 times negative x over x. When x itself is negative, we get 3 times negative negative x divided by x, which is negative. It's confusing, but at the end of the day, whatever number you plug in, try it for yourself, you'll get negative 3. And that's true whenever x is less than 0. So this is the function we're actually dealing with. And now that we've used this definition of absolute value to rewrite the function, it's pretty easy to graph. The y value is 3. And that's true not at 0, but any positive value. And the y value is negative 3. That's true not at 0, but any negative value. And so this is what our graph looks like. Y is either negative 3 or positive 3, depending upon the x value we plugged in. Great. So that was kind of a lot of work to make the sketch, but now that we have the sketch, filling out the info is super easy. So the way to approach these problems in general is kind of flexible. Like on the first problem, I didn't make the sketch until I'd already figured out a lot of information. On the circle problem, I started with the sketch, but that's just because I recognized that this was a semicircle. And if you don't recognize that, then starting with the sketch is not going to work for you. Similar with the square root function, although again, I insist, please recognize the square root function. We spent so much time in IM3 trying to teach you those function families. And they do come up in calculus, and they are very useful to know. Anyway, x-intercepts, none. Y-intercept, none, right? We have these two open circles on the y-axis, but that indicates the function doesn't actually attain a value there. And so there is no output when x is 0, no y-intercept. Domain. Oh, sorry. That's the range. Yeah, let's do range. The range is exactly 2 possible values. Y is 3 or negative 3. That's it. That's the only 2 outputs that this function can take. Domain, every number except for 0. Quickly, this next piecewise function is split up across x equals 0. So on the right side, when x is greater than 0, it's a line with a slope of 1/3 and a y-intercept of negative 2. And to the left, it is a parabola with its vertex at 0, -1. So our graph looks like this. With a decent understanding of parent functions and their transformations, it should be apparent that the x-intercepts are -1 and +6. This particular problem doesn't ask for the x-intercepts, but again, if you wanted to find the x-intercepts, you could do it by just setting these equal to 0 and solving. Actually, this problem doesn't ask for anything except for the graphing, so we're done there. Okay. Let's talk asymptotes. I'm actually going to skip slant asymptotes in these notes. I think it comes up twice, so that we can talk about it in class. I think they're a little more complicated. I want to be there to answer questions as they come up. For what it's worth, this particular function has no slant asymptotes. Horizontal asymptotes. What is a horizontal asymptote? Well, you've seen them before in a couple of different functions. Very first one you've seen is the exponential function, which shows up in IM1. Right, this function basically levels off on the left here. It gets flatter and flatter and closer to usually the x-axis. And so as x gets really far to the left, the y values of the function get really close to the y value of the asymptote. So essentially, to find a horizontal asymptote, one method we could use is just to plug in a really big number. Technically, you need to check the right and the left side. So plug in a really big positive number and plug in a really negative number. This function in math, when you say really big number, it doesn't actually have to be that big. 100's a really big number to a mathematician. Why? Because we're going to square it, and it's going to get really big. Even really or bigger. So what is this? Well, on top, it's 100 times 100, 4 zeros, so 3 followed by 4 zeros. On the bottom, 100 times 100 is a 1 followed by 4 zeros. And now here's sort of the trick. I'm going to claim that this subtraction by 4 does not change the value of this expression very much. And so it's not exactly equal to 3, but it's pretty freaking close. And I could plug in bigger numbers, like 1,000, picking up more zeros, meaning that this subtraction by 4 is even less relevant. So what is the result when we plug in a really, really big number, like 1,000 or 1,000,000 or even bigger? Well, it gets closer and closer to something divided by something that's very, very close to 3. Okay. Another place we've seen horizontal asymptotes is the 1 over x function. On both sides, it sort of levels off towards this, asymptote. And in math analysis, I believe logistic functions you see as well. They have 2 separate horizontal asymptotes, which is why you need to check both the right and the left. On a logistic function, the left side levels off to some asymptote, and then the right side levels off to some other asymptote. Anyway, let's put this asymptote on our sketch as a dotted line at y equals 3. So this function will not, this function will either on the right or on the left, or on the right, and in this case also on the left, I believe, will approach this line, get flatter and flatter and closer to it. Okay. Vertical asymptotes. Vertical asymptotes occur when the bottom of the function is 0 and the top is not 0. Thinking back to our first problem, there was a value, 3, that made the bottom equal to 0. But because the top also evaluated to 0, these two terms sort of canceled out, and the result was that only at 3 do we have a problem, and everywhere else we don't have a problem because the bottom of the fraction is gone. That's why we call it a removable discontinuity. If you have a division by 0 and it's not canceling out with something in the top, you get a more serious discontinuity called an asymptote. And again, this is something we will talk about more later. Here, we have this problem. When I check to see what values could cause the bottom of this fraction to be equal to 0, I get 2 and I get -2. And the top, when I plug in 2 or negative 2, is going to be equal to 12. So I'm going to have an asymptote here. It's okay if we don't fully understand what causes an asymptote versus a removable discontinuity. I'm just telling you now, basically for the first time, that division by 0 causes a discontinuity. One type is called removable, and it shows up on the graph as a singular point that's missing, or a hole. Another type of discontinuity is caused by division by 0, where the numerator is not 0, and that will cause a vertical asymptote. An example you've seen before of this is, again, the 1 over x function. Right? When x is 0, you get 1 divided by 0. And that causes a vertical asymptote, not a hole. This is a joke. It's not a good joke. It's something you see in math textbooks a lot. They'll be doing some kind of explanation, and they'll quit halfway through and say the rest is left as an exercise to the reader, which usually just means the author got lazy and didn't want to finish it. And so we could find the x-intercepts and y-intercepts, and I will leave that as an exercise to the reader. I will say, though, they are both 0. X-intercepts. Okay, let's look at Desmos. This is a no calculator problem. We wouldn't be able to just graph this, but the asymptotes we calculated were correct. And we can see, if we go really far out to the left, the horizontal asymptote and the function get closer and closer. Same is true on the right. The vertical asymptotes, part of the function goes up and approaches the vertical asymptote. Part of the function goes down and approaches the vertical asymptote. How the heck would we sketch this without Desmos? Well, truthfully, I would say, after finding the asymptotes, maybe just make a table of values. Start plugging things in, like 10, 5, 0, -5, -10. And you'll start to sort of pick up some points, and you'll see a pattern. And knowing that the function has to get closer and closer to the asymptotes, and knowing that it has to go through those points, it sort of quickly becomes apparent how your sketch should turn out. Symmetry. This graph has reflectional symmetry across the y-axis. If you were to look at this graph in a mirror, it would look identical. It does not have rotational symmetry, because if you turn your head upside down, it does not look the same. The only other type of symmetry is transformational symmetry, and basically only sine graphs do that, or other trig functions. Basically, if I move the graph like this, it doesn't look the same, right? It's over here. Now it's over here. This next one, I'm not going to go through this. I think I want to do this one in class too. This is an example of a function that does have a slant asymptote. And you can tell because the highest powered term in the numerator and the denominator are not the same power. So in the last example, we had x squared in the numerator, x squared in the denominator. And so when we plugged in super big numbers, they got big at sort of the same pace. And so the numerator was always about 3 times bigger than the denominator. Here, because the numerator is x squared, the top's going to get bigger faster. And so, I mean, the really crude way of thinking about it is x squared divided by x is x. And so you get a slant asymptote meaning an asymptote that isn't vertical, isn't horizontal, but rather follows a diagonal path of y equals x across the graph. Maybe you want to look at this on Desmos if you're curious, or we'll talk about it later in class. Okay, if you have made it this far through the video, congratulations. If you have skipped ahead to this section, welcome. This is the other problem type in our notes packet, along with sort of describing and sketching graphs. The other is solving inequalities. This first example, this could be straight out of an IM2 textbook. Shows up again in IM3, and I do not blame you if you have totally forgotten how to do these. So if you can recall, basically the way we solve these is we treat them like they're equations to find when the left side here is equal to 0. And then we're going to divide a number line into regions. And then in each region, it's either above 0 or below 0. Essentially, we're going to find when the function crosses the x-axis. And then every time it does, we're going to ask it, did you just go under the x-axis or did you just go up and above the x-axis? This is kind of a gnarly factor for a no calculator question. This is probably the hardest of a factoring job you're going to have to do with a no calculator. Every quadratic you see on a no calculator problem is factorable. It is the only method for solving quadratics you need to know. Assuming you have the quadratic formula app on your graphic calculator. Anyway, solving this, we get 5x plus 1 is equal to 0, means x equals negative 1/5. 3x minus 2 equals 0 means x equals 2/3. Okay, so we have negative 1/5. And I know these numbers are kind of gross, but we don't actually have to deal with them. Because remember, we're going to check the regions in between them. So we have 3 regions. We have the left region, the middle region, the right region. Middle, left, right. And so we can plug in any number we want. Any number we want in these regions. We are looking for regions that give us positive values because we were asked when this function is greater than 0. We know this function is 0 at these two, they're called boundary points. I like to plug in 0 because it's usually really easy to plug in 0. 0 happens to live in our middle region. And I'm going to plug in 0 not into the original equation. I'm going to plug it into the factored equation, and we'll see why in a sec. My iPad's being buggy. Now, on a problem like this, fully evaluating is not that hard, right? It's 0 plus 1 is 1 times 0 minus 2 is negative 2. 1 times negative 2 is negative 2. That's negative. Okay. Here's the shortcut I'm going to show you that becomes more useful on more complicated problems. This left term is 0 plus something. And so it is positive. I do not care what number it is. I only care that it's positive. This number, or this term on the right, is 0 minus something. It is negative. I do not care what it is. I care that it is negative. Because, again, I only care if it's bigger or smaller than 0. And so when I multiply a positive times a negative, I get a negative. So in the middle region, it's negative. Again, I'm looking for the region that's positive, that's greater than 0. It's not this one. And so we would check both of the other two regions to make sure which ones are positive or negative. In this particular case, it's a parabola, so, you know, it goes like that, meaning in the purple and the blue regions, it's got to be positive. I will do one more, just if you want to see me do it again. Feel free to skip ahead. And so here, I need to plug in a number bigger than 2/3. Let's pick 1. That sounds nice. This is going to be sort of a better example of the shortcut being kind of useful. And remember, these are no calculator questions, so it's not just a shortcut in the sense that it saves you a little bit of time. It's a shortcut in the sense that it saves you having to do calculations in your head without a calculator. Okay, 5 times 1 is positive, plus 1 is positive. 3 times, it should be a 1. That mess is a 1. 3 times 1 is 6 minus 2 is positive. Positive times a positive is positive. If I were to plug in on the left, I would probably pick -1. Nice, easy number. Okay, this is where we give our final answer. This number line is a visualization of the answer, but the answer itself is, see, everything to the left of -1/5. So x is less than -1/5. Or if it's not to the left of -1/5, then it has to be to the right of 2/3 to be in a positive region. That is the answer to the question. For this next one, I'm not going to do it all the way out, but I will get it into a quadratic just like the last one, and then you would follow the same steps from there. First thing I'm going to do is no, I lied. I'm going to do this one kind of somewhat way through. Okay, first thing I'm going to do is get the right side to be 0. So I'm going to subtract 12x from both sides. And now just like in the last one, I'm going to factor. First thing I want to do, though, is factor out this common x. Take out an x from each term here. And now I can factor this quadratic. Adds to 1, multiplies to -12, minus 3 and plus 4. Okay, so I've discovered my boundary points here. Each of these 3 factors, when you set it equal to 0, gives you a boundary point. So I've got 0, got 3, got -4. A common mistake with a problem like this is to say, first thing I'm going to do is divide everything by x. Problem is, you're forgetting that if you plug in 0, that this equation is true. And so 0 is one of our boundary points. I guess technically I messed up. These should all be equal signs, because we treat it like an equation to figure out when the left side equals 0. And then we use the number line to figure out when it's more than 0 and when it's less than 0. Always a bummer when one of your boundary points is 0, because that means you can't plug it in. It means you have to plug in something gross like 1. So I won't go all the way through here, but you would plug in each region. This time there are 4 regions. There's the left region, this region, and the right region. And you would plug in each one. I do quickly want to discuss the final answer here. So for one thing, we're using the or equals to inequalities rather than strict inequalities, because the original problem had that type of inequality. Basically, if you plug in 0, it is actually a solution. If you plug in -4, it is actually a solution, and so is everything in between. The other thing I wanted to just comment on is, you see this sort of alternating pattern, minus, plus, minus, plus. If you think back to polynomials in IM3 and math analysis, it's a feature of polynomials that these alternate, but it's not guaranteed. If you have a double root, it's not going to hold. If you have a non-polynomial function, it's not going to hold. So technically, at this point right here, I can see I have 3 unique roots, and none of them are double roots. So I know it's going to alternate, but I'm a math teacher, so I don't think the fact that I can tell that necessarily means that you should be able to. So I'm just going to say, check all your regions just to be sure, unless you really paid attention in Chapter 8 and IM3 and you really are confident that you know what's going on. This next one's pretty quick because it's already factored for us. So we have 2x plus 3 is 1 factor, giving us x equals -3/2 when we set that equal to 0. And then we have the other one at just x equals 4. Okay, here's what I meant about double roots and such. I could ask an IM3 student at the end of the year to sketch this function for me, and what they would do is they would say, okay, I see it has a root at 4, and I see it has a root at -3/2, and I can tell the root at -3/2 is a double root, meaning the function bounces off the x-axis, whereas the root at 4 is a triple root, meaning it doesn't bounce, it kind of curves through it. So they would be able to sketch me this function to look like this. And so without testing the points, I can tell negative, negative, positive. I am interested in when this is negative. And so you can totally check the regions manually. You don't need to be this in the weeds with how polynomials work. But my point is, this is a polynomial, and that alternating pattern does not hold for it. This point is not a solution because at that point, the left side and the right side are both 0, and it's a strict inequality. 0 is not less than 0. So I just want to show you how to write the answer here. And it would be everything to the left of -3/2, not including. Or if it's not to the left of -3/2, it needs to be between -3/2 and 4. If this were a strict inequality, the answer would be a lot simpler. It would just be everything that's less than or equal to 4. So for this next one, something different is happening here. We have a denominator. And so when we're making our boundary points, yes, we're still going to make this equation. We're still going to check when this is equal to 0. And that happens when x is 4 or 5. And so these represent x-intercepts. The problem is these are not the only boundary points. When I say boundary points, I mean basically places where the function can switch from being positive to negative. One way that can happen is it crosses through the x-axis, and that's why we look for x-intercepts. Another way this can happen is with a vertical asymptote. And so here I've graphed the function on Desmos, and we can see these x-intercepts at 4 and 5 do cause the function to switch from positive to negative and then back to positive. I'm going to zoom out, and you're going to see that there's 2 more places where the function switches from positive to negative, and they are x equals 3 and x equals negative 3. How did I get those? They are the places where the denominator is equal to 0. If you plug in 3 for x, you get 0 in the denominator. You can't divide by 3. The left side of this equation is undefined. Which means we have some kind of discontinuity. In this case, a asymptote. So here at 3, the function is negative to the left of 3. And it gets more and more negative, and then on the other side of the asymptote, it is positive. So here the function switched from being negative to positive without crossing the x-axis, without leaving behind an x-intercept, but with an asymptote. So when you're looking for your boundary points, x-intercepts and asymptotes are the 2 things you need to check for. I'm not going to do this one out, but your number line should include these 4 numbers, and you need to check. In this case, 1, 2, 3, 4, 5 regions. I'll actually check one region right now because I want to reinforce the fact that this shortcut I showed you earlier is actually very useful. Here, let's check 0 again. So I'm just going to look at these terms. 0 minus 4 is a negative number. 0 minus 5 is a negative number. 0 minus 3 is a negative number. 0 plus 3 is a positive number. On top, I have a negative times a negative, that's positive. On bottom, I have a negative times a positive, that's negative. And so the result is a positive divided by a negative, which is negative. So 0 in this region right here is negative. Since I have to do this 5 times and I don't have a calculator, this is so much better than actually computing the function's output at 0. Because after I do all that work, I'm only checking if it's positive or negative. I don't care if it's 4 or 5 or 10,000. If it's positive, it's positive. If it's negative, it's negative. Okay, last one. This is a cubic, and this is a no calculator question. And we need to somehow solve for the x-intercepts when this is equal to 0. If you have a cubic that you have to solve on a no calculator question, one of 2 things is true. Either, like this one in the top right here, either there's no linear term, and so after factoring out an x, you're left with just a quadratic, or you can solve it with factoring by grouping, which I know is not something that we teach you at this school. I'm going to show you the two ways to do it, the way that the CPM approved way and then the traditional way. So the CPM approved way would be, let's put this in an area model. And absolutely, you cannot solve cubics by just throwing them in a 2x2 area model like this. You would need to use polydoku. If you find yourself doing polydoku on a no calculator question, or honestly ever in this class, then I would recommend that you stop and reconsider. Why are you doing polydoku? You will never have to do it. So this cube is kind of special in that it can be solved with the 2x2 area model. And if you just gave me a random cubic and said, here, solve this, it might not be my first thought to do this method because it's pretty rare that this works. But if I'm taking an AP test, an AP Calc test, and you said, here's a cubic, solve it, this is absolutely the first thing I would do because it's really the only type of cubic that they're going to ask you to solve. And so, ta-da, it's factorable as x squared minus 4 and x plus 3. Difference of squares shortcuts means I have 3 boundary points. X is 2, -2, or -3. Okay. So that's how to do this with an area model. I'll show you how to do it without an area model. Anyone who's self-studied for the 2B or the 2B3 challenge exam, or anyone who's had a tutor, you may have seen this method of factoring before with quadratics. It also works with this type of cubic. So I'm going to take the first term and the third term and write them next to each other. Notice in the area model, these two terms appear here and here. Then I'm going to take the second and fourth terms and put them next to each other. And those appear here and here. I'm doing the same thing with and without the area model. It's just how you visualize it. And so I can factor out an x, and I'm left behind with an x squared minus 4. Looking at the area model, oh look, x squared minus 4, that's right here. Shoot, these are being added together, aren't they? Because I just rearranged them and put parentheses around them. They're being added, not multiplied. Okay, plus, what can I factor out here? I can factor out a 3. What am I left behind with? X squared minus 4. Oh, look, our old friend, x squared minus 4. And check this out. This x and this plus 3 live right here. So this is just factoring with an area model, but not drawing the area model. And so my last step will be to, this is the step right here that freaks people out who've never seen this before. Why am I allowed to do this step? And if that's you right now and you're freaking out and you're saying, I don't know why you're allowed to do that, then I'd recommend to use the area model because I hope that that one makes more sense. All right. this video has been long enough. Hopefully you didn't watch the whole thing. Hopefully I edited it so it's not 55 minutes when I post it. And I will see you tomorrow.